You notice it first in the satellite images, the kind of details the ancient builders never expected anyone from the sky to see. A line of walls in Peru, the base of a temple in Egypt, the foundations beneath a ruined city in Turkey, the stone circles scattered across Japan. Places built by cultures with no shared language, no trade routes, no common mythology, and yet every one of them carries the same mathematical fingerprint, as if following a blueprint older than any empire. Modern geometry detection algorithms, tools designed for robotics, machine vision, and astrophysics, are now being pointed at these ruins. And the results are unsettling. The software keeps flagging identical ratios, repeating harmonics, and recurring geometric signatures. Golden spirals embedded in floor plans, Vesica Piscis patterns hidden in ceremonial platforms, 3 to 4 to 5 triangles determining temple orientations, hexagonal grids structuring entire city layouts. Archaeomathematicians like Alexei Kusenko and Keith Critchlow once suspected these patterns, but seeing them confirmed by machine analysis gives everything a new gravity. Even Kim Malville's work on astronomically aligned sites begins to look like only one piece of a much larger pattern. It forces an uncomfortable question. How did civilizations separated by vast oceans, civilizations that rose and fell without ever hearing of each other, end up building with the same sacred shapes? These aren't vague resemblances, they're precise, measurable, intentional. And when you follow these shapes, when you trace those spirals and overlapping circles across continents, you begin to sense the presence of something deeper, some quiet intelligence woven into architecture itself. Something every ancient builder seemed to understand instinctively, as though geometry wasn't merely a tool, but a language, a way of encoding ideas that long outlived the empires that carved them. You can feel the pull of it now, the way explorers must have felt when they realized the world was far stranger and far more connected than anyone had imagined. Because if these cultures never shared knowledge, then the symbols they used, the ratios they honored, the shapes they repeated, must have come from somewhere else entirely. Whatever that somewhere is, you're about to step into it. The story of humanity's first builders begins long before recorded history, before writing, before metal, before cities. It starts in a place no one expected, a limestone plateau in southeastern Turkey, where the dry wind carries dust across a field of buried circles. When archaeologists first uncovered it, they thought it was a medieval cemetery. It was too elegant, too geometric, too deliberate to belong to the Stone Age. Then they realized what they were looking at. Göbekli Tepe, 12,000 years old, older than the pyramids, older than agriculture, was the first sign that our ancestors crossed a threshold we still don't fully understand. Massive stone circles, each defined with uncanny symmetry, T-shaped pillars arranged in precise arc-like formations, enclosures that follow subtle mathematical rules long before mathematics had a name. These people were hunter-gatherers. They did not farm. They had no cities, no writing, no metal tools. Yet the stone circles they built mirror the geometry of later civilizations by millennia. Once researchers began measuring every pillar, every alignment, every radius, the geometry revealed itself like a ghost emerging from dust. Some of the enclosures form nearly perfect circles, impossible to lay out by chance, especially when each is 10 to 20 meters across. Within these circles, pairs of pillars are oriented towards specific points on the horizon. In 2015, Archaeoastronomy analyzing 3D laser scans noticed something peculiar. The alignments cluster around positions of major celestial events, solstice sunrises, and in some cases, the rising point of visible star groups thousands of years ago. That alone was surprising. But then came the geometric anomalies. When computational archaeologists applied geometry detection algorithms initially developed for architectural forensics, the hidden structure of Göbekli Tepe began to surface. Several enclosures fit inside phi-based circles, The circumference and radius follow the golden ratio within a margin more precise than anything expected from Stone Age builders. Some pillar pairs form isosceles triangles whose tips aim toward astronomical targets. And most striking of all, a three-point collinearity pattern, three key pillars lying on a perfect straight line, appears repeatedly across the site. That line, when extended, intersects distant horizons where important star risings occurred in 10,000 BCE. This wasn't random placement, this was intent, memory, design, and Göbekli Tepe wasn't alone. Across Europe, where the Neolithic world was still young and restless, groups of early builders were shaping landscapes with geometry so subtle it remained unnoticed for millennia. On the windswept plains of Brittany, the Karnak alignments stretch across kilometers, thousands of stones placed in rows so straight that modern surveying equipment struggles to find any deviation. For decades, researchers dismissed them as ritual markers or territorial boundaries. Then mathematicians began studying their spatial patterns using collinearity analysis software. What emerged was a hidden scaffolding. Many lines form exact multiples of 30, 60, or 90 degrees relative to one another, angles found in hexagonal geometry. Some of the alignments generate triangles with 3 to 4 to 5 proportions, the same right-angled triangle used in Egyptian pyramids thousands of years later. These geometric patterns were not visible from the ground. They were only obvious from above. Yet the builders knew where each stone needed to stand. Further north, at the Ring of Brodgar and the stones of Stennis in Orkney, researchers used drone photogrammetry to measure planarity and curvature. What they found shocked even conservative archaeologists. The circles deviate from true circularity by such small margins that only a deliberate mathematical framework could explain them. The outer Ring of Brodgar fits a 60-sided circular geometry, essentially a hexagonal system scaled outward into smooth curvature. Again, this was long before writing, long before numbers, but the geometry was already alive. As more sites were scanned, a startling picture emerged. Neolithic builders across Europe seemed to share an internalized map of shapes, circles, alignments, triangles, and harmonic ratios, without any contact between regions. Archaeomathematicians began to suspect a deeper pattern. When those theories were compared with data from Göbekli Tepe, something clicked. The same geometric habits existed thousands of years earlier, thousands of miles away. This was not a later invention, it was a continuation of an older memory. And then came the megalithic sites with dimensions tied to phi. At Newgrange in Ireland, a passage tomb older than Stonehenge, the ratio of the chamber width to the height of its corbelled dome closely approximates the golden ratio. Its entrance stone contains spirals carved with a precision that suggests more than artistry. Some follow logarithmic curves, tightening inward in smooth mathematical spirals. In 2020, a team using curve-fitting software showed that several megalithic spirals align within 1 to 3% of a true golden spiral. Margin of error comparable to Bronze Age metalwork, not Neolithic stone carving. Across the sea in Malta, the temples of Hagar Kim and Menajdra have ellipsoidal plans that archaeologists once called oddly organic. But when mathematicians analyzed their floor plans, they discovered that the ellipses correspond to specific ratios between major and minor axes, ratios that appear again in later Mediterranean architecture. Menajdra Temple in particular contains an internal division whose proportions map almost exactly to 1 to the square root of 3, a ratio foundational to later hexagonal geometry. These builders were not merely placing stones, they were shaping space according to patterns that resonate across civilizations, and each discovery only sharpened the paradox. As the millennia unfolded, later cultures inherited, expanded, or reinvented these geometric ideas. But they didn't create them. They stepped into a stream that already had momentum, a current of mathematical imagination originating somewhere deep in prehistory. Egypt provides one of the clearest examples. By the time the Old Kingdom rose around 2600 BCE, geometry was no longer intuitive, it was explicit. Scribal schools taught rope stretchers how to create perfect 3 to 4 to 5 triangles. Architects used sekheads, slope ratios, to define pyramid angles. But several pyramid dimensions reveal something older. Phi appears again and again, not by coincidence but by deliberate design. The Great Pyramid's half-base to height ratio closely approximates phi. The bent pyramid's change of angle corresponds to geometric harmonics. Even the alignment to true north is so precise it suggests a long tradition of astronomical geometry. But Egypt was not the origin. It was an inheritor. And the same principle echoes in the earliest cultures of the Indus Valley, where uniform grid plans appear in cities like Mohenjo-Daro and Harappa. Archaeologists discovered that city blocks follow a recurring ratio, 1 to the square root of 3, again linking to hexagonal geometry. Standardized bricks were made in precise 1 to 2 to 4 proportions. Drainage channels align according to reciprocal angles. Even early seals contain mandala-like patterns structured on nested circles. China's Neolithic Liangzhu culture built jade bi-discs with perfect circularity long before bronze tools. Their ritual axes often contain hidden 3 to 4 to 5 triangles. And when laser scanning was applied to Liangzhu levees and waterworks, researchers found geometric planning embedded in the hydraulic layout. Across the Pacific in ancient Japan, the Asuka alignment and Kofun burial mounds follow axial geometries whose angles mirror those in Western megalithic sites, despite complete cultural isolation. Someone, somewhere, charting the dawn of civilization, had already learned to see the world as a series of relationships, circles, alignments, ratios, harmonics. And that vision spread not by conquest, not by writing, but by human memory carried across generations. The more archaeologists scanned, measured, and compared, the more the similarities piled up. But the turning point came when computational geometry entered the field. Programs originally created for robotics, designed to detect edges, curves, and symmetries, were repurposed for archaeology. When researchers fed satellite imagery and 3D scans of ruins into these algorithms, the software detected repeating motifs with clinical impersonality. It didn't care about cultural boundaries, languages, or chronology. It simply saw patterns. And what it saw looked like the world's oldest architectural signature. Circles subdivided into 60 segments, triangles locked into 3 to 4 to 5 proportions, spirals following phi, collinear rows pointing to solar or stellar points, ellipses whose axes followed geometric series, ratios that reappeared not once but thousands of times. In every region, in every period, in every culture, from Göbekli Tepe's hunter-gatherers to Egypt's pharaohs, from Orkney's stone circles to Indus Valley grids, the same shapes waited beneath dust and soil. This was humanity crossing the threshold, the moment the world shifted from survival to imagination. When the ancestors who once followed herds began to follow patterns, when stones became symbols, when geometry stopped being something embedded in nature and began to be something humans could embed into nature. And quietly, in the margins of this ancient story, later civilizations, Islamic astronomers, Persian architects, Andalusian geographers, would inherit and refine these early ideas, turning spirals into cosmograms, triangles into star maps, circles into sacred diagrams. Their moment will come later in the journey, but the roots are already here, planted deep in forgotten soil. The deeper researchers dig, the more one question presses against the mind. Was this geometry invented by scattered tribes, emerging independently again and again like sparks across the dark? Or was it remembered, echoes of a much older understanding carried through time before the first stones were ever raised? The ruins do not answer, but their symmetry suggests that humanity did not stumble into mathematics. It stepped across a boundary, into a world where shapes held meaning, where numbers were not abstractions but truths written into the bones of the earth. And someone, thousands of years before history began, was already reading them. Long before the Mediterranean glistened with the scattered civilizations of Greece and Rome, long before the vast empires of Mesopotamia fully realized the mathematics hidden in their ziggurats, Egypt rose along the banks of the Nile, a river that shaped life, commerce, and thought with quiet inevitability. It was a land that demanded precision. The Nile flooded predictably each year, depositing fertile silt across the desert floor, but the river's rhythms also created a challenge. The land shifted, boundaries blurred, and the flat plains could betray the careless surveyor. It was here that geometry first became not merely a tool, but a sacred instrument, a language through which humans could impose order on chaos. The Egyptians were masters of observation, not only of the heavens and the river, but of the very earth beneath their feet. And when they began building monuments intended to last through eternity, that observational skill crystallized into mathematics. It is impossible to study the pyramids without noticing that they are far more than tombs. They are calculations rendered in stone, architectural symphonies of proportion, alignment, and scale. The Great Pyramid of Giza, Khufu's masterpiece, exemplifies this perfection. Surveyors and archaeologists, including Mark Lehner and Glenn Dash, have spent decades meticulously recording the base and height of the pyramids, comparing measurements, angles, and relationships between the stones. Their research confirms that the Great Pyramid's dimensions are not arbitrary. The ratio of the half base to the height approximates the golden ratio, a mathematical relationship that would captivate Greek philosophers centuries later. Whether the builders understood it consciously as a ratio or as a proportion derived from practice remains debated, but the precision is undeniable. The limestone casing stones, some polished to reflect sunlight, were cut and laid to form near-perfect angles, with errors so small they challenge modern surveyors. The 3 to 4 to 5 triangle emerges here as the most elegant and practical of tools. Known in ancient Egypt as the sekhed, it allowed builders to establish right angles with ropes marked into 3, 4, and 5 units. By stretching the rope across the ground and measuring the diagonal, they could create a perfectly square base for a pyramid or temple. This simple principle is nothing less than applied trigonometry, centuries before formal trigonometric tables existed. Jean-Philippe Lauer, among others, has shown that the careful use of these triangles enabled the construction of pyramids, mortuary temples, and causeways, aligned not just to each other, but to points on the horizon with astronomical significance. The orientation of the Great Pyramid to true north, accurate within a fraction of a degree, suggests that this was no accident. Surveyors used stars, particularly the circumpolar stars, as guides, translating celestial observation into terrestrial geometry. The Nile itself shaped these constructions. Every year, as the river rose and fell, land boundaries shifted. Egyptian surveyors, or rope stretchers, measured plots with taut ropes, ensuring that temples and tombs maintained proper alignment and proportion despite environmental changes. Archaeologists like Lehner and Dash have documented how survey markers in nearby quarries correspond with the axes of pyramids, reflecting a continuous dialogue between measurement, ritual, and space. The land itself became a canvas for mathematical imagination. But the genius of Egyptian geometry is not limited to triangles and linear measurements. Circular forms appear in temple designs, sunken courts, and mortuary enclosures, often in proportions echoing the golden ratio. The pyramid's base, when doubled and compared with the perimeter, reveals a subtle harmonic relationship that seems to anticipate the logarithmic spirals found in nature. Researchers in the 20th century, revisiting survey records and employing photogrammetry, discovered that the spacing between shafts and chambers often corresponds to proportions that repeat in smaller and larger scales. A fractal-like sensibility, embedded long before fractals were formally conceived. Egypt's understanding of space and geometry was deeply entwined with its culture and worldview. The pharaohs were not only kings, they were intermediaries between the human and divine realms. Architecture was theology, geometry was devotion. Temples were constructed as microcosms of the universe, pyramids as eternal stairways to the stars. The use of right angles, equilateral triangles, and proportional grids was more than functional. It was a statement that order could emerge from chaos, that the cosmos could be mirrored on Earth through human skill. The golden ratio was not merely aesthetic, it symbolized harmony, a reflection of Ma'at, the principle of truth, balance, and cosmic order that governed every aspect of Egyptian life. Surveying techniques in ancient Egypt further demonstrate their mastery. Rope stretching is often mentioned in texts and inscriptions, but the practical application was far more sophisticated than mere linear measurement. Teams of surveyors could measure large distances, calculate slopes, and lay foundations on uneven terrain while maintaining proportional consistency. Archaeologist Jean-Philippe Lohr notes that quarries often contain pre-cut stone blocks with dimensions precisely matched to the intended pyramid segment, suggesting a pre-visualized plan using these geometric rules. Some stones reveal faint markings indicating divisions into thirds or quarters, a method that would allow builders to scale up simple triangles into massive structures while preserving right angles and proportional ratios. It is here that the first true mathematical empire reveals itself, a civilization capable of encoding complex geometric relationships into structures that would endure for millennia. Egyptian mastery is not limited to a single pyramid or temple, it pervades the landscape. Causeways, satellite pyramids, mortuary temples, and alignment with natural features, rivers, hills, and plateaus, create an entire spatial network governed by proportion and harmony. When viewed from above, these arrangements resemble giant geometric patterns etched into the desert, a visual manifestation of intellectual control over space, matter, and light. The 3 to 4 to 5 triangle particularly serves as a connective thread across time. While the Egyptians used it primarily for construction, later civilizations encountered the same proportions independently. Mesopotamian surveyors applied similar triangles in city planning. Greek philosophers codified them in theory. Indus Valley engineers incorporated them in urban grids. Neolithic Europeans used them to align stones over vast distances. The recurring presence of this triangle across cultures separated by oceans and centuries raises a profound question. Did humans discover these ratios independently through observation, or did they inherit an intuitive understanding of geometry that stretches back beyond recorded history? Modern investigations have provided further evidence. In the 1970s, Glenn Dash conducted detailed surveys of the Great Pyramid's base, using laser theodolites to measure corner angles and sides with millimeter precision. His data confirmed previous estimates, but revealed subtler alignments, diagonal relationships that match the 3 to 4 to 5 proportions, suggesting deliberate embedding of harmonic triangles across scales. Dash argued that such precision could not have been accidental. These triangles, it seems, were a conceptual scaffold upon which the Egyptians built not just stone, but cosmic meaning. The golden ratio also permeates Egyptian design, though its use was rarely documented in texts. Architectural historian Adolf Ehrman noted in the early 20th century that the dimensions of the Great Pyramid appear to encode when the height is compared to the half base. More recently, computer simulations and 3D modeling by researchers such as John Ligon have confirmed these findings, indicating that the ancient builders may have understood proportional relationships far deeper than previously thought. Their use is subtle, almost invisible to the casual observer, yet consistent enough to suggest intentionality rather than coincidence. Yet the Egyptians were not merely calculating for calculation's sake. Their geometry served ritual, orientation, and cosmic reflection. Temples faced solstices and equinoxes, Obelisks and causeways aligned with star risings. Chambers inside pyramids were oriented towards circumpolar stars. In all cases, geometry became the invisible hand tying the earthly realm to the heavens. The physical form of a pyramid, a rectangle, a triangle, a spiral, was inseparable from the metaphysical meaning it carried. Space was both measured and sanctified. It is in this duality, practical and sacred, that Egypt becomes a masterclass for the world. Its builders were both surveyors and philosophers, measuring rope stretchers and metaphysicians. The techniques developed here, right triangles, proportional baselines, harmonic ratios, precise orientations, would echo across millennia. Islamic scholars would later codify similar principles in architecture and astronomy. Greek mathematicians would formalize them as abstract theory. But Egypt did not merely transmit mathematics, it embodied it, allowing geometry to shape human experience directly. And yet, even as the pyramids rise, the question emerges again, more urgently than ever. Across continents, among cultures that never exchanged words or tools, similar triangles, spirals and ratios appear. Why does the 3-4-5 triangle show up in Europe, India, and even Neolithic Japan? Is it a natural consequence of observation and human perception, an intuitive discovery repeated independently? Or does it hint at something deeper, a shared understanding embedded in the human mind, or perhaps whispered by the natural world itself? The Egyptians provide no direct answer. Their texts speak of kings and gods, not of geometric theory. But the stones, the angles, and the invisible grids they left behind speak loudly enough for those who know how to read them. They tell us that humanity, even in its infancy, had already begun a conversation with mathematics. They reveal a civilization crossing a threshold from survival to conceptual thought, from reliance on the river and the hunt to a conscious shaping of space and meaning. Geometry became not a tool for living, but a language for understanding, a lens through which the universe could be interpreted and reflected on Earth. And when we trace the echoes of these triangles, the resonance of, and the grids embedded in the sands of Giza across continents and centuries, we realize that Egypt's lesson was not merely technical, it was philosophical. Geometry was a bridge between the mortal and the eternal, between humans and the cosmos, between what is seen and what is known. The land of the Nile, with its shimmering horizon, its measured floodplains and its monumental stones, had become the first classroom in cosmic geometry. The 3-4-5 triangle was more than a mathematical tool. It was a symbol, a thread that would weave through every civilization daring enough to measure, build, and aspire. And in that geometry, the first architects of the impossible left an invitation, a challenge to all who followed to look beyond mere survival, to measure not just stone, but the universe itself. Long before the Nile carved its path through Egypt, long before stone circles crowned the hills of Europe, the land between the Tigris and Euphrates, Mesopotamia, was already whispering the secrets of the heavens. Here, amid fertile plains and shifting rivers, humans began to codify time and space, not merely as practical measures, but as reflections of cosmic order. Babylon, Ur, and Nippur became the laboratories of the first mathematicians, astronomers, and architects, a civilization where calculation and observation were inseparable. Mesopotamia was a land of layered complexity. The rivers dictated life, flooding unpredictably and reshaping the earth. Yet in this chaos, humans sought order in the heavens. Babylonian scholars developed a numerical system based on 60, a sexagesimal system that would shape mathematics, timekeeping, and eventually the geometry of the universe itself. Unlike the base 10 systems familiar today, base 60 allowed unprecedented flexibility in expressing fractions and ratios, enabling them to model planetary motion with surprising precision. Every circle was divided into 60 parts, every hour into 60 minutes, every minute into 60 seconds. In a sense, the number 60 became a bridge between the terrestrial and the celestial. It is within this framework that architecture, mathematics, and cosmology began to converge. The ziggurats, stepped pyramids rising above city landscapes, were not merely temples. They were physical manifestations of layered cosmograms, microcosms of the heavens themselves. Each level represented a plane of existence, each ascent a movement closer to the divine. Scholars such as Stephanie Daly and Paul Collins have analyzed the alignment and proportions of ziggurats, showing that their dimensions often correspond to astronomical intervals, the rising and setting of stars, the lunar cycle, and the paths of planets visible to the naked eye. Vesica Piscis forms, those overlapping circles revered across millennia, appear repeatedly in Mesopotamian temple layouts. In some Sumerian precincts, twin enclosures trace elliptical or vesica-like shapes, their axes aligned with solstitial points on the horizon. Modern archaeologists using satellite mapping and LIDAR technology have confirmed these orientations with remarkable accuracy. What is striking is the intentionality. These geometric forms were not aesthetic afterthoughts. They encoded celestial knowledge, a dialogue between earthly structures and cosmic patterns. Among the most astonishing relics of this civilization are the clay tablets, the artifacts of human thought baked into permanence. Plimpton 322, a tablet from approximately 1800 BCE, contains a table of numbers that mathematicians now recognize as Proto-Pythagorean triples. Rows of numbers correspond to the sides of right triangles, demonstrating an understanding of geometric principles centuries before Pythagoras himself was born. Researchers such as Eleanor Robson have painstakingly analyzed these tablets, showing that Babylonian scribes were capable of manipulating complex ratios, solving problems of distance and angle for architecture, land division, and astronomy. The connection between numbers and the sky was explicit. Planetary cycles, Venus, Mars, Jupiter, Saturn, were recorded with geometric proportions, their periods encoded in tables that could be applied to both ritual timing and practical governance. When modern software simulates these cycles using Babylonian ratios, the correlation with observed astronomical events is striking. For example, Venus's synodic cycle, approximated as 584 days, aligns with divisions of ziggurat steps, while lunar eclipses and solstices are often encoded in the layout of temple courtyards. Geometry here was a lens through which humans could model time and anticipate the rhythm of the cosmos. The intellectual ripples from Mesopotamia would eventually reach far beyond its cities. Greek philosophers traveling to Babylon or reading translations inherited the base 60 fractions, the triangular knowledge, and the harmonic ratios. Thales and Pythagoras drew upon these ideas, developing the theorems and abstractions that form the core of classical geometry. Later, Islamic scholars in Baghdad, particularly during the House of Wisdom in the 9th and 10th centuries, codified Babylonian astronomical observations, refining them into trigonometric tables and cosmographic maps. Here again, the geometry of the heavens influenced human architecture now in mosques and observatories, mirroring patterns first recorded on clay tablets. Even the layout of the ziggurats carries echoes of these ratios. Archaeologists using photogrammetry and digital reconstruction software have found that the step heights and platform widths correspond with sequences derived from base 60 calculations. At Ur, the Great Ziggurat rises in measured proportions that approximate harmonic triangles. When viewed from above, the stepped terraces form concentric geometric layers, almost like rings echoing outward from the sacred core, repeating the patterns of spheres and ellipses that chart the motion of celestial bodies. These forms seem to encode knowledge of both the earth and sky, suggesting that the Babylonians understood geometry as a bridge between mortal and cosmic order. It is easy to dismiss these structures as religious symbolism, but the evidence points to something more profound. Every alignment, every ratio, every proportional relationship is measurable and repeatable. The Babylonians did not rely on intuition alone. They quantified, tabulated, and applied these principles systematically. Even ceremonial spaces for offerings and public gatherings obeyed geometric constraints, suggesting that mathematics was woven into the rhythm of daily life. Geometry was the language through which the Babylonians understood their world, both mundane and sacred. Clay tablets extend this insight into abstract theory. Beyond Plimpton 322, other tablets describe procedures for calculating areas, volumes, and slopes, often using triangular subdivisions or reciprocal calculations. The reciprocal tablet, for instance, presents a method for dividing a field into equal areas using geometric reasoning. While the problems are practical, the approach is undeniably theoretical. It requires abstraction, visualization, and proportional thinking. It is an early form of applied mathematics, evidence that humans were thinking in terms of geometric relationships long before Euclid would codify them in Alexandria. Planetary cycles encoded on these tablets also reveal a sophisticated interplay between geometry and observation. The Babylonians recognized that certain ratios repeat predictably: the orbit of the moon against the backdrop of stars, the intervals of Jupiter and Saturn, even the complex synodic cycle of Venus. When modern simulations compare these ratios with historical alignments of ziggurats and temple orientations, the correlation is remarkable. The structures themselves become tools for observing the sky, a marriage of architecture and astronomy. Geometry was no longer static, it was predictive. The intellectual tradition that began here laid the groundwork for civilizations millennia later. Greek mathematicians refined triangles and circles into deductive reasoning. Islamic astronomers translated Babylonian tables into Arabic, built observatories in Baghdad and Samarkand, and developed trigonometry for predicting celestial motion. The influence persists today in modern geometry, navigation, and even computer modeling of orbital mechanics. The Babylonians, largely forgotten in popular memory, created a mathematical language that survived empires, conquests, and centuries of change. It is easy to marvel at their skill, but one question presses: why did geometry arise here, at this specific crossroads of rivers, mud, and sky? Was it necessity alone, the need to divide land, measure time, or build temples? Or was there a deeper inspiration, drawn from the very motion of the heavens? The evidence suggests the latter. From the alignment of ziggurats to the proportion of temples and the ratios encoded in clay, the Babylonians seem to observe the universe and attempt to bring its order down to earth. Each mathematical discovery, each carefully laid stone, was a translation of cosmic movement into human comprehension. And the patterns do not stop at the heavens. Some researchers have noted that even everyday items, weights, measures, and pottery follow proportional relationships reflecting the same harmonic ratios found in monumental architecture. Babylon was a laboratory not just for kings and priests, but for the very notion that the universe could be measured, predicted, and embodied in tangible form. The legacy of Mesopotamian geometry stretches further. When the Greeks encountered Babylonian knowledge, they did not simply adopt it, they refined it. Thales and Pythagoras, whether through travel or study, inherited base 60 fractional reasoning and the early understanding of right triangles. Plato would later codify the abstract forms of geometry, but the practical application, the living, breathing mathematics, had already been demonstrated on the banks of the Euphrates. Later Islamic scholars preserved, expanded, and transmitted this knowledge, developing trigonometric methods that would eventually underpin celestial navigation, architectural design, and even modern physics. And yet, as impressive as this mathematical foresight was, it leaves us with a question as old as the ziggurats themselves. If humans first applied geometry by observing the heavens, by translating the movements of stars and planets into forms, then does it follow that every geometric structure on Earth is a reflection of the sky? Did triangles, circles, spirals, and harmonic ratios arise first from the heavens, or were they discovered independently on Earth and then projected upward? Were the Babylonian priests and builders responding to a cosmic code, reading the sky as one reads a manuscript, or inventing a language of proportion that happened to resonate with the universe? Perhaps it was both. The mathematics of Babylon shows us that human thought can abstract, quantify, and encode the world, while simultaneously being inspired by the patterns inherent in nature. In observing the heavens, they found principles of geometry, and in geometry they mirrored the heavens. Each ziggurat, each temple, each clay tablet becomes part of a continuum, linking human intellect to the stars and to all civilizations that would follow in their footsteps. From Mesopotamia, the language of geometry begins its long journey, crossing continents, oceans, and centuries. The patterns embedded here, triangles that measure angles, circles that chart time, proportional grids that harmonize the sacred and the mundane, appear again and again in distant lands, in cultures with no direct contact. Greece, Egypt, the Indus Valley, and later Islamic cities all inherit echoes of this mathematical vision. The trials of the Mesopotamian mathematicians and builders, their meticulous measurements and celestial observations, become the scaffolding upon which the architecture of the ancient world rests. And as we trace these lines from clay tablet to ziggurat, from riverbank to temple, we are forced to wonder, was geometry first a tool, a practical invention for earthly concerns, or was it always a reflection of something greater, a universal order revealed by watching the heavens themselves? After the rivers of Mesopotamia carved their fertile plains and the Nile sculpted its endless horizon, human thought began to turn inward, seeking not only to measure the world, but to understand its underlying principles. Greece emerged as the first civilization to treat geometry not merely as a tool of builders, priests, or astronomers, but as a philosophy, a lens through which the cosmos itself could be interpreted. Here, mathematics became an instrument of thought, a dialogue between the mind and the structure of reality, and the human imagination stepped fully onto the stage of abstraction. The figure of Pythagoras looms large over this transformation. Born on the island of Samos around 570 BCE, he traveled extensively, likely to Egypt, Babylon, and possibly even farther east, absorbing knowledge that would be reinterpreted through Greek reasoning. Pythagoras is often credited with formalizing the relationships between numbers and shapes, yet what he and his followers produced was far more than theorems. It was a vision of the universe as a living, harmonious system, a cosmos in which mathematics was both music and structure. Numbers were not mere counters, but the essence of being, and shapes were the visible manifestation of numerical harmony. The Pythagorean school believed that everything in existence could be expressed through ratios, proportions, and geometrical forms. It was in this intellectual atmosphere that the first Platonic solids, tetrahedron, cube, octahedron, dodecahedron, icosahedron, were conceptualized. Plato, a student of Socrates and a philosopher deeply concerned with the nature of reality, later codified these solids in his dialogues, connecting them to the elements: fire, earth, air, water, and the cosmos itself. These forms were not arbitrary. They were the geometry of existence, the skeleton of creation. The tetrahedron, with its sharp triangular faces, embodied the dynamism of fire, the cube, stability and permanence of earth. The universe, it seemed, was structured according to mathematical law. But abstract geometry in Greece did not emerge in a vacuum. Egyptian and Mesopotamian mathematics, absorbed through travel, trade, and observation, provided a foundation. The right-angled triangles of Egypt, the sexagesimal ratios of Babylon, and the observational precision of their temples and ziggurats informed Greek thought, even if only as inspiration rather than direct replication. Greek mathematicians distilled these practical applications into theoretical frameworks. Euclid, in Alexandria centuries later, would codify these principles into the elements, creating a system that combined logic, deduction, and spatial reasoning in a way the ancient world had never seen. Within the Hellenic world, geometry became a mirror of both nature and mind. The Greeks observed spirals in shells, the branching of trees, the arrangement of petals, and noted the ratios inherent in these forms. The golden ratio, already encoded into Egyptian monuments and possibly even earlier Neolithic structures, was now recognized as a principle of harmony and proportion, a bridge between natural forms and human understanding. Architects, sculptors, and city planners began to embed these ratios into temples, theaters, and public spaces, translating abstract thought into tangible experience. This period also saw the application of geometry to the heavens in ways that rivaled Mesopotamian astronomy. Hipparchus and later Ptolemy built models of celestial spheres, using geometric constructs to predict planetary motion. Concentric circles, epicycles, and harmonic relationships mapped the heavens onto a framework of points, lines, and angles. It is here that the Greeks expanded the notion of geometry from earthly measurements to cosmic patterns. Geometry became a universal language, capable of describing both the stones of a temple and the stars above, uniting terrestrial and celestial knowledge into a coherent vision. The architectural manifestations of these ideas were subtle but profound. Greek temples, for instance, employed proportional systems derived from Pythagorean ratios. The Parthenon in Athens, constructed in the 5th century BCE, exemplifies this approach. Its facade, columns, and spacing embody ratios that approximate, producing a sense of harmony and visual balance. Even the curvature of the stylobate, the platform on which columns stand, was adjusted to counter optical illusions, demonstrating a sophisticated understanding of perception, proportion, and geometry. Here, mathematics, art, and philosophy converge. Greek philosophers also speculated on the metaphysical implications of geometry. Plato's notion of the world of forms posited that every object in the material world is a reflection of a perfect, abstract geometric idea. The physical world, while beautiful and complex, is only a shadow of ideal mathematical forms that exist in an eternal realm. This philosophical stance cast geometry as not only a practical tool, but as a window into the eternal, a way to perceive the underlying order of reality. Numbers and shapes were no longer just measurements, they were manifestations of cosmic truth. The Pythagoreans extended these insights into music, discovering that harmonious intervals correspond to simple ratios of string lengths. The octave, fifth, and fourth, foundational to musical scales, emerge from ratios such as 2:1, 3:2, and 4:3. This realization bridged mathematics, physics, and philosophy. Harmony in sound reflected harmony in form. The universe itself seemed to resonate with geometric and numerical patterns, echoing across matter, energy, and perception. From the motion of planets to the spirals of shells, from architectural grids to human experience, the principle of proportion reigned supreme. Greek geometry also introduced rigorous proof, establishing a method for validating relationships between shapes and numbers. Unlike the practical geometry of Egypt or the observational tables of Babylon, Greek mathematics demanded logical certainty. Euclid's postulates provided a foundation upon which future civilizations could build, extending from architecture to astronomy to theoretical physics. This system of reasoning transformed geometry into a universal language, one that could travel across space and time, independent of culture, language, or geography. And yet, as powerful as Greek abstraction was, it remained rooted in observation. Plato and the Pythagoreans did not float in a vacuum of pure theory. They observed the world and the heavens, noting recurring proportions, symmetries, and patterns. They codified and idealized what earlier civilizations had discovered practically. In doing so, they created a bridge between applied geometry, used by Egyptians, Mesopotamians, and Neolithic builders, and a philosophical framework that would inform every subsequent civilization interested in cosmic order. The Hellenic expansion of geometry was both intellectual and cultural. Alexander's conquest spread Greek thought across Egypt, Persia, and India, merging traditions and enabling cross-cultural exchanges. Greek architecture influenced cities from Asia Minor to Egypt, and Greek astronomical concepts informed later Islamic scholars in Baghdad, Cordoba, and Samarkand. Geometry became a lens through which humans could interpret the universe, a shared language capable of connecting distant minds across time and space. And here, in this transmission of ideas, the hero's journey advances. Humanity had crossed the threshold in prehistory, learning to see geometry in stones and stars. Mesopotamia had codified ratios and cycles, embedding them in temples and tablets. Egypt had encoded harmony and the golden ratio in monuments that reached toward eternity. Now Greece distilled these lessons into philosophy and abstraction, providing the mind itself as the instrument for exploring cosmic order. Geometry had evolved from observation into thought, from applied tool into universal language. Yet questions linger, as they have since the earliest days of Göbekli Tepe and the Nile floodplains. If right triangles, spirals, and harmonic proportions appear independently across cultures, why do they recur with such consistency? Is there a deeper principle, a cosmic architecture that predates human thought? Did the Babylonians, Egyptians, and Greeks merely observe, record, and perfect what already existed in the universe? Or does human consciousness possess an innate ability to perceive and enact these patterns, a kind of mathematical intuition encoded in our cognition? Greek geometry provides a tantalizing clue. Its rigorous methods, philosophical depth, and cosmological vision suggest that mathematics is not merely a human invention, nor purely a tool for survival. It is a way of reading the universe, a way of translating celestial and terrestrial order into a language we can understand. Numbers, ratios, and shapes become a bridge between the finite and infinite, the ephemeral and eternal. In studying Greek mathematics, we glimpse a civilization stepping fully into the world of ideas, teaching humanity not just how to build or measure, but how to think, how to see, and how to connect. And in that vision, the legacy of all previous civilizations, Neolithic builders, Egyptian surveyors, Babylonian astronomers, finds a form. Geometry is no longer hidden in stone circles or temple foundations. It is abstracted, codified, and ready to inspire every subsequent civilization that would inherit it. From Greek philosophy, the path is clear. Mathematics is universal, timeless, and capable of bridging continents and epochs. Every triangle, every circle, every ratio carries meaning far beyond the hands that first drew it in the sand or carved it in stone. But as the Greeks taught, knowledge is never static. With this abstraction comes a responsibility, a challenge to explore further, to apply these principles not only to architecture or astronomy, but to thought itself. And it is precisely this challenge that will be taken up by civilizations far to the east and west, particularly the brilliant minds of the Islamic Golden Age, who will inherit, translate, and expand upon Greek geometry in ways that echo across centuries. The ideas of Plato, Pythagoras, and Euclid become a bridge spanning continents, connecting the stones of the past to the minds of the future. And yet, as we trace these lines from Greece back to the ziggurats of Babylon and the pyramids of Egypt, one question remains pressing. If geometry can be observed, codified, and abstracted independently across time and space, what does that say about the origins of these patterns? Did humanity invent geometry as a response to nature, or did we discover a pre-existing cosmic order, one that has been quietly guiding minds from the very dawn of civilization? Long before steel cranes and modern surveying instruments, human civilizations across the vast reaches of Asia were uncovering the invisible skeleton of the cosmos, embedding it into temples, palaces, and urban layouts. From the sacred plains of India to the fertile valleys of China, geometry was not simply a tool of construction. It was the language of the universe, a lens through which the very structure of existence could be perceived, measured, and enacted. Here in the East, the principles first glimpsed in Egypt and Mesopotamia found a new expression, one that was both spiritual and practical, abstract and tangible, deeply human, yet cosmically inspired. In India, geometry was inseparable from spirituality. The earliest sacred diagrams, mandalas, served as cosmic maps, visualizations of the universe itself. These were not mere artistic patterns. They encoded philosophical principles, astronomical observations, and mathematical precision. Mandalas often consist of concentric circles, squares, and nested triangles, each layer representing a plane of existence or a stage of consciousness. Scholars such as Sarvapalli Radhakrishnan and modern researchers in archaeomathematics have shown that the construction of mandalas follows precise ratios, sometimes approximating the golden ratio and exhibiting radial symmetry that mirrors celestial motion. When a devotee meditates upon a mandala, they are not only contemplating divinity, they are engaging with a mathematically structured cosmos, a dialogue between human perception and universal order. The Sri Yantra, perhaps the most sophisticated of these geometric constructs, is composed of 9 interlocking triangles, creating 43 smaller triangles in a precise pattern. It is a visual representation of the cosmos, a map of the energy forces that govern both matter and consciousness. Recent studies using digital reconstruction have demonstrated that the angles and intersections within the Sri Yantra correspond to ratios that approximate, creating a dynamic interplay of symmetry and proportion. Constructed on temple floors or etched into sacred diagrams, it served as both a spiritual tool and a blueprint for cosmic harmony. Here, geometry is not abstract. It is experiential, meditative, and alive, a means to align human activity with the larger rhythms of the universe. Vastu Shastra, the ancient Indian system of architecture, further codified geometry into lived space. Its principles dictate orientation, proportions, and layout based on cosmic laws, ensuring that buildings harmonize with the natural and celestial order. Temples, homes, and city plans were designed according to these laws, creating a spatial order that reflects both aesthetic and metaphysical concerns. Researchers in cultural archaeology have noted that ancient cities such as Mohenjo-Daro and later urban developments in South India exhibit vastu-aligned grids where streets, courtyards, and sacred spaces follow proportional relationships derived from simple ratios, triangles, and squares. Here again, we see geometry emerging as a universal language, one that unites practical architecture with philosophical insight. Far to the north and east in China, geometry found expression in entirely different, yet equally sophisticated forms. Bronze vessels of the Shang and Zhou dynasties display hexagonal patterns, suggesting an early understanding of tessellation and symmetry. These patterns were not mere decoration. They encoded ritual, cosmology, and social hierarchy. The hexagon, with its inherent efficiency and tessellating ability, may have also been a mathematical insight applied to both material and conceptual structures. Archaeologists and materials scientists studying Tang and Han-era artifacts have identified ratios and proportions that hint at like relationships, suggesting that ancient Chinese artisans were sensitive to harmonic proportions long before they were formally described in the West. The Forbidden City, completed during the Ming Dynasty, is perhaps the most iconic demonstration of cosmological grid planning in China. Its vast complex, with a perfect axial symmetry stretching over 7 square kilometers, reflects principles of balance and order derived from both astronomy and philosophy. Researchers in architectural history have shown that the placement of gates, halls, and courtyards follows precise modular ratios, echoing the cardinal points and aligning with celestial bodies. Even the orientation of the Hall of Supreme Harmony aligns with solstitial sunrises, embedding cosmic rhythms into urban space. Mathematics, in this case, is inseparable from ritual and governance. It is geometry in service of cosmic, social, and political harmony. Further illustrating this, the I Ching, the ancient Book of Changes, encodes binary patterns that map onto hexagrams, 6-line symbols representing cosmic processes. Scholars have noted that the underlying mathematics of the I Ching, combining symmetry, inversion, and reflection, is inherently geometric, demonstrating an early grasp of combinatorial structures and duality. In effect, these are algorithms of balance and transformation, translating abstract cosmic principles into tangible symbolic forms. Just as Babylonian tablets encoded planetary cycles, so too does the I Ching encode principles of change and proportion, bridging mathematics, cosmology, and philosophy. When we compare India and China, we see distinct cosmologies, yet a convergence in their geometric understanding. Triangles, circles, grids, and ratios recur across thousands of miles, separated by mountains, deserts, and oceans. In both regions, sacred structures are aligned to celestial events, proportional grids govern urban layouts, and symbolic patterns encode philosophical and astronomical knowledge. The geometry may manifest differently, the Sri Yantra in India, the hexagonal tessellations in China, but the underlying principle is the same. The universe can be understood and expressed through form, ratio, and symmetry. Light touches of Islamic influence begin to appear in later centuries, particularly in India, where the fusion of geometric knowledge finds its most luminous expression in Mughal architecture. The Taj Mahal, with its perfect symmetry, central dome, and proportioned gardens, draws upon both indigenous Vastu and mandala principles and the inherited mathematics of Islamic artisans who had themselves absorbed Greek, Babylonian, and Indian ideas. Here, geometry transcends cultural origin. It becomes a shared language, a bridge between civilizations separated by time, religion, and geography, yet united by a vision of cosmic order. The repetition of proportions, the embedding of symmetry into lived space, and the echoing of sacred forms illustrate that human societies independently converged upon the same geometric truths. Yet even amid this flourishing, a question emerges. How could such precision, such harmonic resonance appear in civilizations that were often unaware of one another? The Sri Yantra, the Forbidden City, and Babylonian ziggurats were constructed independently, yet they share ratios, patterns, and alignments that hint at a universal grammar of form. Are these coincidences or evidence of a deeper principle guiding human cognition? A geometric intuition encoded within the very act of observation, measurement, and design? Did humanity, dispersed across continents, independently arrive at the same truths because they are embedded in nature, in perception, or even in the cosmos itself? Archaeomathematics research has begun to quantify these parallels. Studies comparing Tang dynasty architecture, Indian mandalas, and even European Gothic cathedrals reveal recurring ratios, sometimes approximating, sometimes simple harmonic divisions of 2 to 3 or 3 to 4 to 5. These ratios are applied to spatial dimensions, proportions between elements, and alignments with the horizon. Digital modeling and laser scanning allow modern scholars to trace these geometric fingerprints with unprecedented precision, confirming that ancient architects, far from working arbitrarily, were following rules of symmetry, proportion, and cosmic reflection. Geometry emerges as both practical toolkit and philosophical inquiry, a bridge between human construction and universal pattern. And so, the journey continues. From the Neolithic stone circles to Egyptian pyramids, from Mesopotamian ziggurats to Greek abstraction, and now to the sacred grids of India and China, humanity steps further into the world of mathematical imagination. Triangles, circles, hexagons, nested grids, these forms recur across the globe, often independently, sometimes influenced by exchange, but always demonstrating an uncanny resonance with the cosmos. They hint at a truth deeper than culture, religion, or geography, a truth embedded in observation, cognition, and perhaps the universe itself. As we trace these forms from east to west, one realization becomes undeniable. Despite differing cosmologies, philosophies, and spiritual systems, the geometry is consistent. It is a silent thread woven through human history, connecting disparate civilizations in their quest to understand, mirror, and inhabit the cosmos. Different rituals, different myths, different languages, yet the same ratios, the same harmonics, the same pursuit of proportion balance, and resonance. Across time and space, humanity seems to have stumbled upon, or perhaps remembered, a universal blueprint. Long before European explorers crossed the Atlantic, civilizations in the Americas had already begun charting the cosmos, encoding its rhythms in stone, earth, and sky. These societies, separated by oceans from Eurasia for millennia, developed intricate systems of knowledge that, astonishingly, mirror geometric principles found in Africa, the Near East, and Asia. Triangles, spirals, ratios, and cosmic grids appear again, not through transmission or trade, but through independent observation, intuition, and invention. The Americas, it seems, held their own sacred code, written in geometry. In the lowlands of Mesoamerica, the Maya civilization flourished, leaving behind cities, temples, and calendars that reflect extraordinary mathematical sophistication. Maya astronomers observed the Sun, Moon, Venus, and other planets with incredible precision, recording cycles in codices, inscriptions, and monumental architecture. Anthony Aveni, a leading archaeoastronomer, has shown that Maya temples and observatories are aligned to celestial events, solstices, equinoxes, and the movements of Venus, with a precision rivaling contemporary Old World civilizations. The pyramid temples at Uxmal and Copan, for instance, follow precise angular relationships, creating terraces and platforms that encode solar geometry. The Maya also developed mandala-like cosmograms, circular or square arrangements of sacred spaces that reflect cosmic order. Linda Shaley, one of the foremost experts on Maya iconography, emphasized that these layouts were not mere decoration. They were maps of the universe, connecting human activity to celestial cycles. Circles, radial axes, and nested triangles appear repeatedly, suggesting a deep understanding of geometric relationships. Some researchers note that the ratios embedded in these structures, including the heights of pyramids relative to their base dimensions, approximate the Golden Ratio, a striking parallel to Egypt, Mesopotamia, and Greece. Far to the north, in the Valley of Mexico, Teotihuacan rose as one of the most meticulously planned cities in pre-Columbian history. Its main avenues, pyramids, and plazas follow precise axial alignments that correspond to solar risings and settings. The Pyramid of the Sun, one of the largest in the Americas, sits on an axis slightly offset from true north, aligned instead with the point of the Sun on certain ritual dates. Archaeologists have noted that the placement of pyramids, residential compounds, and ceremonial spaces repeatedly employs triangular and modular divisions, creating a geometric network across the city. Research in archaeoastronomy, particularly by Clive Ruggles, demonstrates that Teotihuacan's planners applied consistent geometric ratios in the orientation of streets, plazas, and pyramids, reflecting an understanding of the interplay between earth and sky. Moving westward into the Andes, the Inca civilization presents yet another astonishing application of geometry. Inca architects, without the use of mortar, constructed polygonal walls with astonishing precision. Stones fit together so perfectly that even a knife blade cannot be inserted between them. Scholars such as John H. Rowe and Terence N. Daltroy have documented that these polygonal walls often employ geometric angles that create stability and harmony, effectively combining structural necessity with aesthetic proportionality. At Machu Picchu, the terraces, temples, and residences follow patterns that mirror the contours of the landscape. Yet within those contours, ratios appear that echo the principles seen in other distant civilizations: triangles, proportional divisions, and orientation aligned with solstices. Even temple terraces, from Ollantaytambo to Sacsayhuaman, reveal phi-like ratios in their step heights and horizontal dimensions. Researchers employing photogrammetry and 3D modeling have demonstrated that the Inca were consciously creating harmonious ratios, likely derived from observation of natural forms and celestial events. Solar alignment was a key factor. Windows, doorways, and platforms correspond to sunrises on solstices and equinoxes, ensuring that sacred architecture resonated with cosmic rhythms. The repeated appearance of these ratios across structures separated by hundreds of kilometers suggests a coherent geometric tradition embedded in the collective understanding of the Inca people. The question arises, how did these principles emerge in complete isolation from Eurasian civilizations? While the Americas were separated by vast oceans, the recurrence of golden ratios, triangular grids, and cosmological alignments implies a universality to geometric thinking. Are these ratios simply the most efficient way to stabilize structures and orient them to the sun and stars? Or is there something deeper, a cognitive or natural imperative that guides humans towards certain geometric forms when attempting to reconcile architecture with the cosmos? Anthony Aveni argues that human observation of celestial cycles inevitably leads to certain geometric constructions. Solstices, equinoxes, and planetary motions provide reference points that naturally suggest axial alignments, triangular divisions, and harmonic ratios. When humans observe regular patterns in the sky, they unconsciously impose similar patterns in architecture. In this sense, geometry is not entirely invented. It is discovered, emerging as a natural response to the cosmos. Yet the sophistication and consistency of these applications in Maya, Teotihuacan, and Inca architecture surpass what would be expected from casual observation alone. The ratios and alignments are precise, repeated and integrated into city planning, temple construction, and landscape modification, a testament to deliberate mathematical insight. Linda Sheely also emphasizes that Maya geometric cosmograms encode spiritual and ritual meaning. The alignment of temples with stars, the proportion of pyramids, and the orientation of plazas were all intended to connect humans with the cycles of the universe. In Teotihuacan, Ruggles notes, geometric patterns reflect a similar concern. City planning was ritualized, sacred space encoded in the fabric of daily life. Inca terraces and temples similarly embed cosmological principles. Across the Americas, geometry functions as both practical and symbolic language, enabling humans to navigate physical space while simultaneously interpreting the cosmos. The parallel with Eurasian civilizations is striking. Across continents and millennia, the same patterns recur: triangular divisions, concentric circles, axial alignments, phi ratios, and grids that mirror celestial order. And yet, the Americas had no contact with Egypt, Mesopotamia, Greece, or India during these periods. The repetition of geometric forms is not a result of diffusion, it is independent emergence. This raises profound questions about human cognition and perception. Is there an innate capacity in the human mind to recognize, reproduce, and apply certain geometric forms? Are triangles, spirals, and proportional grids instinctive solutions to the challenges of structure, orientation, and alignment with natural cycles? Or do these forms exist in nature itself, whispering their ratios and symmetries to any attentive observer, regardless of culture or location?
Modern archaeomathematics provides insight into these questions. High-precision mapping, 3D modeling, and satellite surveys allow researchers to detect patterns that were previously invisible. Photogrammetry of Maya pyramids, LiDAR scans of Teotihuacan, and drone surveys of Inca terraces reveal systematic ratios and alignments. Statistical analysis confirms that many of these proportions approximate or simple harmonic fractions. Such precision suggests intentionality rather than coincidence, yet the same ratios also appear in natural forms: crystals, flowers, shells, and spiral galaxies, hinting at a universal logic inherent in both nature and human cognition.
This convergence of observation, intuition, and calculation illustrates a broader principle. Geometry emerges wherever humans seek to reconcile space, time, and the cosmos. The Americas demonstrate that this emergence is independent, robust, and culturally specific, yet echoing patterns seen worldwide. From the ziggurats of Babylon to the Sri Yantra of India, from Egyptian pyramids to Inca terraces, the same principles recur, suggesting a shared cognitive or cosmic source. As we contemplate these mirror empires of the Americas, the narrative tension deepens. How can societies so separated by distance, language, and history arrive at the same geometric truths? Is geometry a universal language embedded in the human mind, waiting to be discovered? Or is it a reflection of natural laws, whispering itself into existence through observation and practice? The Americas offer no easy answers, only evidence of astonishing human ingenuity and an uncanny resonance with the cosmos. In this stage of our journey, humanity confronts the idea that geometry may be innate, a bridge between cognition and nature, between the earth beneath our feet and the heavens above. The pyramids, terraces, and temples of the Maya, Teotihuacan, and Inca civilizations stand as silent testament. Even in isolation, humans reach toward the same geometric truths, discovering patterns that transcend culture, geography, and time. And as the Americas reveal their mirror empires, one question lingers, haunting every stone, every terrace, every temple. Are these forms the product of human invention, shaped by observation and necessity, or are they whispers of a universal order, a cosmic geometry waiting to be recognized wherever a civilization dares to look to the sky and measure its rhythms? Across continents and millennia, a remarkable pattern emerges. Geometry is not merely a tool or an ornament, it is a language. From the pyramids of Egypt to the terraces of the Inca, from the mandalas of India to the grids of ancient China, and into the early mosques and madrasas of the Islamic world, sacred geometry surfaces repeatedly, a universal grammar written into stone, earth, and sky. But what is it saying? What are these forms trying to communicate? In the most basic sense, sacred geometry functions as a language of proportion. Triangles, circles, and grids are not arbitrary. They convey relationships, ratios, and harmonies that can be read across cultures. A vesica piscis here, a nested triangle there, a phi-based spiral elsewhere. These patterns express order and alignment, echoing structures seen in nature, shells, flowers, and the spiral of galaxies. Human perception recognizes and reproduces them instinctively, yet the results often exceed practical necessity. They are both practical and poetic, measurable, yet imbued with symbolic resonance. At the same time, geometry serves as a map of the heavens. Ancient astronomers, whether in Babylon, Maya cities, or the observatories of India and China, encoded the paths of the sun, moon, and planets into architectural grids. Temples, pyramids, and civic layouts frequently align with solstices, equinoxes, and lunar cycles. These alignments suggest that geometry was more than decoration or convenience. It was a tool to chart the cosmos, a method of bringing celestial order into human experience. Rites, rituals, and city life became inseparable from these mathematical rhythms. Geometry also functions as a symbol of spiritual thought. In Egypt, the pyramids' proportions reflect divine harmony, the convergence of earth and sky. In India, the Sri Yantra embodies cosmic energies, nested in precise triangles that represent creation and dissolution. Taoist cosmograms in China articulate the flow of heaven and earth through symmetry, reflection, and pattern. Even early Islamic art, constrained by aniconism, translates the metaphysical principle of Tawhid, unity of God, into endlessly repeating geometric motifs where symmetry and proportion express spiritual oneness. In each case, geometry mediates between the human and the divine, grounding abstract philosophy and form. Philosophy, too, interprets geometry as a universal code. Plato argued that forms, the eternal perfect realities behind the material world, exist in geometric order. To study a triangle, a circle, a sphere, is to glimpse the underlying truth of existence. In Hindu thought, Artha, the cosmic order, is reflected in proportion, symmetry, and the regulation of time and space. The universe itself is encoded in measurement, ritual, and temple architecture. Taoist cosmology similarly envisions the Tao as a flowing structure, an invisible pattern underlying the harmony of heaven, earth, and humanity. Across traditions, geometry becomes a medium through which humans perceive the cosmos, whether as divine principle, universal law, or philosophical truth. Viewed this way, sacred geometry is almost like a cosmic instruction manual. It suggests that the universe itself is structured, legible, and intelligible to human observation. Builders, astronomers, and priests across disparate civilizations seem to have tapped into this instruction set, consciously or intuitively. The repetition of triangles, circles, hexagons, and spirals in cultures that had no contact, Egypt and the Maya, India and China, Persia and the Islamic world, implies that these forms emerge wherever human consciousness interacts with the cosmos. Modern research reinforces this. Computational analyses of ancient sites, from Göbekli Tepe to Machu Picchu, show that ratios and alignments are not coincidental. Archaeomathematics reveals recurring proportions, phi-based lengths, 3 to 4 to 5 triangles, hexagonal grids, embedded in structures used for both ritual and practical purposes. Cosmograms, whether etched on stone or mapped into city layouts, consistently translate astronomical cycles into geometric form. These findings hint at a universality. Geometry is a language that transcends culture, geography, and time, one that humans instinctively speak when seeking to understand the cosmos. Yet an enduring question remains. Did ancient builders and astronomers merely notice patterns in nature, codifying them into sacred architecture? Or did they somehow decode laws inherent to the universe itself, hidden in the proportions and rotations of planets, the harmonics of sound, and the spiral of galaxies? Was there a shared intuition, a cognitive resonance with cosmic order, that guided disparate civilizations to the same geometric solutions? In this revelation, geometry is no longer incidental. It is a medium of understanding, a bridge linking architecture, astronomy, philosophy, and spirituality. It is simultaneously human and universal, practical and metaphysical. The stones, terraces, mandalas, and grids are more than monuments. They are a testament to humanity's attempt to read the invisible, to find order in chaos, and to mirror the cosmos in our constructions. As we step back to observe this pattern emerging across continents and epochs, one question dominates the horizon. Did ancient civilizations independently discover these geometric laws, or were they listening in some way to a code written into the universe itself? Beneath the surface of ancient monuments, hidden in plain sight, lies a lattice of proportion and symmetry that only now, with modern tools, can be revealed. For centuries, the stones of Angkor Wat, Borobudur, Petra, the desert cities of the Middle East, and the great monuments of Egypt seemed mute. Their perfection was admired, but partial. It took the 21st century to unlock the geometries they had encoded, not by chisels, but with light, particles, data, and algorithms. In 2012, a turning point arrived. Archaeologists, long frustrated by the jungle canopy hiding the ruins of the Khmer Empire, secured airborne access, a helicopter flying over central Cambodia, scanning the terrain with LiDAR. Over days, the machine fired millions of laser pulses. When the data returned, researchers found not fragments of monuments, but an entire city. Dozens of temples, reservoirs, causeways, embankments, and habitation zones across some 300 square kilometers stood revealed, structures invisible to explorers on foot or from the ground. This was the first truly large-scale archaeological LiDAR survey in Asia. Its revelations forced a dramatic reinterpretation of the scale, ambition, and planning of the Khmer Empire. No longer a collection of isolated temples, Angkor appeared as a planned urban complex where geometry shaped not just pyramids, but rivers, cities, waterworks, and human lives. These LiDAR maps provided the terrain, But to read the hidden geometry, the alignments, ratios, spirals, modular grids, archaeologists turned to photogrammetry and 3D reconstruction. Drone flights captured temple complexes from multiple angles. Ground surveys recorded the layout of stones, foundations, and causeways. At Southeast Asian sites, but also in other regions, researchers began building digital models, geometric skeletons of lost cities. These models revealed proportional relations not obvious in the field, terraces arranged in radial modules, platforms subdivided into nested rectangles, causeways aligned along axes corresponding to solar or lunar paths, and repeating modules that echoed harmonic subdivisions. These are 1 to 2, 2 to 3, 3 to 4, even approximations of the golden ratio. As these datasets multiplied, a new tool entered the archaeologist's toolbox: machine learning and pattern recognition. In 2023, a paper titled "Archaeological Sites Detection with a Human-AI Collaboration Workflow" described how deep learning models, originally developed for urban planning and remote sensing, could be adapted to detect buried structures in landscapes. By running semantic segmentation on satellite and aerial imagery, the algorithm flagged potential archaeological features, enclosures, walls, avenues, which human experts then verified on the ground. The system achieved detection accuracy near 80%, transforming months of fieldwork into weeks of scanning. But beyond simply spotting ruins, more advanced workflows began to analyze geometry itself. Using 3D reconstructions from LiDAR and photogrammetry, researchers developed software capable of extracting angles, alignments, and proportions, automatically scanning entire temple complexes for spirals, right triangles, rectangular grids, and nested modules. When fed data from Angkor, Petra, and other sites, the algorithms returned a startling pattern. Many structures across unrelated cultures employed similar geometric templates. Rectangular galleries split by right angles, temples arranged around central squares, adaptations of circle-square layouts, repeated proportional relationships echoing simple harmonic divisions. In parallel, particle physics entered the field of archaeology. In December 2015, a team led by physicist Kunihiro Morishima at Nagoya University placed muon detectors inside the Queen's Chamber of the Great Pyramid of Giza, that was built circa 2560 BCE under Pharaoh Khufu. Muons that are subatomic particles born when cosmic rays strike Earth's atmosphere pass through rock, but their absorption varies with material density. By measuring muon flux from multiple directions, scientists reconstruct a density map. Where muons pass more freely, there must be voids. In March 2016, after months of data collection, the first anomalies appeared.
From 2016 to 2017, two further independent detection methods happened. These were scintillator hodoscopes from Japan's KEK and gas detectors from France's CEA. They confirmed the anomaly. In November 2017, the team announced the discovery of a large, previously unknown cavity above the Grand Gallery. The so-called Big Void, at least 30 meters long, with a cross-section comparable to the Grand Gallery itself. It was the first major internal structure discovered in the pyramid since the 19th century.
This wasn't a subtle crack. It was a large volumetric anomaly, invisible to the naked eye, undetectable by traditional archaeology, but laid bare by muon radiography. It transformed the Great Pyramid from a solid monolith to a structure with hidden chambers, potentially part of an internal architectural geometry long lost to history. The combination of modern technologies, LiDAR mapping, photogrammetric reconstruction, AI geometry detection, muon tomography, creates a powerful new paradigm. No longer must archaeologists rely solely on fragments, ruins, and fragments of history. They can reconstruct entire cities, overlay internal and external geometry, and analyze global patterns statistically. At Angkor Wat, for example, digital reconstructions show that the central temple, its satellite temples, reservoirs, and causeways form a nested geometry. a central square grid surrounded by water-filled moats, further encircled by radial causeways and terraces, as though the city had been designed as a living cosmogram. When AI-based ratio analysis is applied, distances and angular relationships conform repeatedly to 1 to 2, 2 to 3, 3 to 4 proportions, with hints of golden ratio divisions between successive layers. The repeating modules suggest a hierarchical structure: local temples, regional centers, waterworks, all based on a common geometric template. Similarly, in Petra, digital topography and 3D mapping reveal that tomb facades, theaters, and communal structures align to equinox sunrise directions. The triangular pediments of tomb facades correspond to 3 to 4 to 5 triangles. The spacing between tombs and plazas falls on modular grids. Digital reconstruction suggests that the city's plan was not ad hoc, but followed a coherent mathematical design, blending cosmic alignment with civic layout. In the Islamic world, early Abbasid constructions, mosques, madrasas, and urban layouts present circle-square symmetries, domes of exact diameters, courtyards of proportional ratios, minaret placements that respect axial symmetry. When 3D models are analyzed, these elements appear not as isolated aesthetic choices, but as part of a structured, recursive geometry, one that echoes the same patterns detected in Angkor, Petra, and many other ancient sites. Some architectural historians, such as those inspired by the work of Keith Critchlow and Salim al-Hassani, argue that this geometry expresses metaphysical principles: unity, cosmic order, divine harmony. Modern techniques only reinforce that interpretation, showing that these spiritual ideals found expression in precise mathematical form repeated over centuries. The recursive nature of the geometry is especially striking. In multiple sites, Angkor, Petra, early Islamic complexes, researchers observe what one might call geometric fractals. A larger temple mirrors the proportions of smaller satellite temples. A city's layout mirrors the geometry of a sacred center. Courtyards, domes, and decorative elements follow the same ratios at different scales. In statistical analysis, these recurrences are rarely random. The probability that so many proportions, alignments, and ratios would overlap by chance is vanishingly small. As one archaeogeometry puts it, repetition is a fingerprint, a guiding principle. In 2024, further advances pushed the frontier again. Improved muon tomography simulations demonstrated that with 2 planar detectors placed on adjacent sides of a large pyramid, it is theoretically possible to achieve sub-meter resolution of internal structures. Trials suggest that future imaging could reach resolution of roughly 3 meters in central slices, enough to reveal narrow corridors, hidden shafts, or even internal chambers previously inaccessible. At the same time, archaeologists are building predictive models. By feeding data, known alignments, module sizes, harmonic ratios, into algorithmic templates, they can forecast where undiscovered temples, satellite shrines, or buried structures might exist. In the jungles of Southeast Asia, such predictions have already led to new findings: remote mounds, hidden terraces, water management features once obscured by centuries of overgrowth. These discoveries suggest that ancient builders didn't only produce static monuments, they produced entire networks, entire landscapes shaped by geometry aligned to water, land, and sky. What emerges from all this is a paradigm shift. Geometry was not an afterthought or a decorative flourish. It was the underlying language of ancient construction, planning, cosmology, and spirituality. The same conceptual framework emerges independently in Cambodia, Jordan, Indonesia, Egypt, and the Islamic world. The recurrence across cultures, continents, and epochs suggests not diffusion or imitation, but convergent emergence. Human cognition, when faced with architecture, astronomy, ritual, and landscape, seems to arrive repeatedly at the same set of forms: squares, circles, triangles, spirals, grids, nested modules. The tools of the modern era, lasers, drones, cosmic particles, neural networks, are not just revealing secrets. They are reading an architecture of thought, encoded in stone, earth, and silence. These technologies have become time machines, dissecting history layer by layer, uncovering voids, realigning lost cities, restoring hidden geometries, and revealing a cosmic code older than writing. And standing before this reconstruction, the question becomes unavoidable. Did ancient builders everywhere stumble upon the same mathematical language by instinct? Or were they listening to something deeper? A geometry not of their making but of the universe itself? A cosmic instruction manual written in angles, ratios, and alignment, waiting for minds alive enough to read it. As the detectors hum, the lasers scan, the algorithms map, and the models render, we realize that the monuments of the ancient world are not silent relics of vanished cultures. They are living manuscripts, and at last, we are learning to read them. Beneath the patterns of stone and civilization, the world itself speaks in geometry. Look closely, and one begins to see that the forms embedded in temples, pyramids, and mosques are not inventions of human whimsy, but echoes of the cosmos itself. Hexagons, vesica piscis, spirals. These shapes emerge repeatedly, not only in architecture, but in nature, across scales both vast and minute. The hexagon, for instance, appears in the swirling storms atop Saturn's North Pole, a six-sided vortex larger than Earth itself, spinning in perfect symmetry, captured in stunning detail by NASA's Cassini spacecraft in 2013. The planet's atmosphere, shaped by fluid dynamics and planetary rotation, spontaneously organizes into this geometric perfection. On our own planet, bees construct honeycombs, six-sided cells that maximize storage while minimizing wax. Basalt columns like those of the Giant's Causeway in Northern Ireland or Devil's Postpile in California form naturally as volcanic rock cools and contracts, breaking into hexagonal prisms. The same shape, repeated across worlds and scales, hints at a universal principle, that energy, force, and efficiency often converge on this simple, harmonious form. Equally pervasive is the vesica piscis, two overlapping circles forming a pointed oval. It appears in the arrangement of seeds within fruit, in the overlapping wakes of rippling water, even in wave interference patterns in physics. The form is not merely aesthetic, it is a natural solution to optimization, growth, and propagation. It is the template for expansion and balance. When architects in India drew the Sri Yantra, or when Islamic builders layered interlocking domes, they may have been consciously or intuitively echoing this universal pattern, translating the language of nature into stone. Spirals, too, dominate both the heavens and the earth. Galaxies curve in logarithmic spirals, hurricanes spin in immense cyclonic arcs, and the Nautilus shell coils in the same proportionately expanding form that has fascinated mathematicians for centuries. Darcy Thompson, in his 1917 seminal work on growth and form, demonstrated that biological shapes often follow simple mathematical rules, revealing the deep order underlying living forms. Decades later, Alan Turing's 1952 work on morphogenesis mathematically described how patterns such as stripes, spots, and spirals emerge from chemical gradients and reaction diffusion systems. Together, these insights suggest that the forms ancient builders encoded were not arbitrary. They were reflections of fundamental processes that govern matter, energy, and life itself. Across continents, one sees the same motifs repeating. In Angkor, the alignment of temple terraces echoes the concentric circles and vesica structures seen in seed patterns. In Petra, the triangular faces of tombs recall the fractal precision of naturally forming hexagonal columns. In Gothic and early Islamic architecture, repeating spirals and interlaced vesicas dominate the ornamental designs, a visual language bridging earth, sky, and human imagination. The implications are profound. Humanity, it seems, was not imposing geometry upon the world. It was observing, imitating, and translating nature's instructions into enduring structures. Every column, terrace, and dome becomes a cipher, a testimony that human creativity and the laws of physics are entwined. Yet even as we map these patterns, measure the angles, and trace spirals from galaxies to shells, the question lingers: what other geometries does nature whisper that we have yet to recognize? What universal forms remain hidden, waiting for the next observer to notice and translate? The monuments, the storms, the seeds, the shells, they all hum the same song, a cosmic symmetry that predates humanity, yet has shaped its vision. And as we follow this thread, one cannot help but wonder, are we uncovering a universal blueprint, or merely glimpsing fragments of an infinite, elegant order that will always remain partially beyond our reach? Across the world, humanity has long been captivated by the power of repetition, pattern, and interlocking forms. Tessellation, the art of covering a surface with shapes without gaps or overlaps, emerges as a striking testimony to both aesthetic sensibility and mathematical insight. From the mosaics of Rome to the latticework of China, the interlocking motifs of Greece, and the intricate Islamic giri tiles, civilizations separated by time, culture, and geography have repeatedly returned to the same geometric ideas. Roman artisans, for instance, mastered the use of tessellation in mosaic floors dating back to the 1st century BCE. In Pompeii, Herculaneum, and Ostia, mosaics depict not only mythological scenes, but also geometric precision. Hexagons, squares, octagons, and nested triangles interlock seamlessly across entire floors. Scholars have noted that the Romans were aware of harmonic proportions, often applying ratios derived from the Pythagorean tradition to achieve visual balance. These patterns, while decorative, also reflect a deep understanding of geometry as a tool for spatial organization. Greek architects and artisans, particularly in the Hellenistic period, developed interlocking motifs that combined aesthetic rhythm with structural logic. Pavements in Greek sanctuaries, such as those at Delos and Kos, demonstrate complex grids of triangles, rhombuses, and star polygons. Here, tessellation was not merely ornamental, it encoded proportion, harmony, and the subtle mathematics of light and shadow across surfaces. These patterns are early expressions of the same geometric consciousness later codified in Islamic art. Across the Pacific, Japan cultivated its own tessellated forms. The Asanoha pattern, dating back centuries, consists of interlocking 6-pointed star shapes derived from overlapping triangles. Used in textiles, temple decorations, and screens, it simultaneously embodies structural efficiency and symbolic meaning. The pattern often represents growth, resilience, and protection. Despite the geographical isolation from Mediterranean civilizations, the same fascination with repeating geometric forms emerges, suggesting that the human mind naturally converges on efficient, symmetrical structures. China, too, developed a rich tradition of tessellation. Latticework, particularly in the Ming and Qing dynasties, features interlocking squares, octagons, and meandering geometric motifs. These designs are more than decoration. They regulate light and airflow, create structural integrity, and encode philosophical symbolism. The repetition of geometric patterns in Chinese architecture and artifacts parallels the symbolic and functional integration seen in Roman and Japanese tessellations. Islamic tessellations represent perhaps the most sophisticated application of interlocking geometry. Beginning in the 8th century, artisans across the Middle East began producing patterns that combined mathematical precision with symbolic resonance. Giri tiles, interlocking decagons, pentagons, and bow ties, could be arranged to create 5, 8, and 10-fold symmetries. These patterns extend endlessly, suggesting infinity, unity, and divine order. Scholars such as Keith Critchlow and the Princeton research team have demonstrated that some of these quasi-crystalline arrangements predate Roger Penrose's 20th century discoveries, indicating that medieval artisans intuitively understood complex, non-repeating tiling. When we compare these tessellation systems, a remarkable convergence emerges. Despite differences in culture, function, and medium, the same geometric principles recur: repetition, modularity, symmetry, and the interplay of simple forms to create complex wholes. Whether in Roman mosaics, Greek floors, Japanese textiles, Chinese screens, or Islamic architecture, tessellation manifests as both a cognitive achievement and a visual philosophy. It is a demonstration of human capacity to recognize, manipulate, and celebrate the underlying order of space. The Princeton studies on medieval Islamic quasi-crystals reveal the staggering sophistication of these artisans. By analyzing the geometry of Giri tiles and their arrangements, researchers found that patterns incorporate non-periodic symmetries, forms that do not repeat in a simple translational way, yet are bound by strict mathematical rules. These findings suggest that medieval craftsmen, centuries before formal mathematical proofs, understood how to orchestrate complex modular systems that remain visually and structurally coherent. The global recurrence of tessellation hints at a deeper question. Are these patterns invented consciously, discovered intuitively, or inevitable outcomes of the human mind interacting with space, material, and the constraints of perception? Roman mosaics may have been consciously designed for visual delight, Japanese asanoha for symbolic meaning, Islamic Giri tiles for spiritual contemplation, yet all converge on the same geometric principles. Perhaps there exists a universal geometric imagination emerging wherever humans engage with symmetry, proportion, and spatial reasoning. Through tessellation, we see the subtle bridge between the visible and the invisible. These patterns, covering floors, walls, and ceilings, are not merely ornamental. They are codified reflections of cosmic order, visual expressions of mathematical truth. Just as nature employs hexagons, spirals, and vesicas, human civilizations have independently translated universal forms into art and architecture. Tessellation becomes a language that transcends culture, era, and geography, revealing a collective intuition that the world can be ordered, repeated, and harmonized. As we step back to observe mosaics, lattices, and Giri patterns, we confront a profound realization. The recurrence of geometric imagination is so consistent, so elegant, that it feels as if the human mind itself is tuned to discover and manifest these patterns. Across continents and centuries, we see the same rhythm of shapes, the same pursuit of proportion, the same celebration of symmetry, and yet the mystery endures. Were these tessellations consciously invented, discovered through observation of nature, or simply inevitable when humans engage with the challenge of space and pattern? Across thousands of years, from Rome to Japan to Samara, the answer is elusive. Perhaps the truth lies somewhere in between, that human creativity, inspired by the forms of the universe, repeatedly returns to the same principles, echoing a geometry that is at once natural, intellectual, and transcendent. In observing these tessellations, we realize that geometry is more than decoration, more than utility. It is a master key, opening doors to understanding not only human cognition, but our deep, innate connection to the cosmos itself. And as we continue our journey, one question looms. If these patterns are inevitable, what other universal forms remain hidden, waiting for the observant eye to bring them to light? For millennia, humans have not only built with stone and timber, they have built with the sky in mind. From the earliest megaliths to the grand pyramids, from Maya observatories to Chinese imperial cities, geometry has served as a bridge between Earth and cosmos. It is a language of alignment, a method of encoding celestial cycles into the very bones of our civilizations. Stonehenge, standing on the windswept Salisbury Plain, is perhaps the most iconic testament to this principle. The massive sarsen stones, arranged in a precise circular pattern, align with the rising sun at the summer solstice and the setting sun at the winter solstice. Archaeologists and archaeoastronomers, including Gerald Hawkins in the 1960s and later Mike Parker Pearson, used statistical analysis to confirm that these alignments are far beyond chance. Every stone, every avenue, every gap corresponds to the solar path across the sky. What appears as a prehistoric circle of stone is in fact a gigantic calculator, marking the rhythm of the seasons, the solar year, and even lunar cycles. Across the Mediterranean, the Egyptian pyramids also testify to this celestial obsession. Surveyors working for Mark Lehner and Glenn Dash have confirmed that the sides of the Great Pyramid are oriented almost perfectly to the cardinal points. Beyond simple compass alignment, the internal passageways correspond to stellar risings. The southern shaft of the King's Chamber aligns with the Belt of Orion, a constellation intimately tied to Osiris and the afterlife. Solstice and equinox lines were embedded in the causeways and temple complexes, ensuring that every movement of the sun or star could be traced from earth to heaven. These architectural decisions required both a profound understanding of geometry and precise observational astronomy, illustrating that ancient builders were adept mathematicians as much as religious visionaries. The Maya, too, encoded the heavens into their monumental architecture. Zenith passages, the days when the sun passes directly overhead, were meticulously observed at sites such as Uxmal and Copan. The alignment of pyramids, plazas, and ball courts reflects these observations, creating cosmograms that functioned as both ceremonial spaces and astronomical instruments. Anthony Aveni and Linda Shaler have documented how these alignments tracked solar and lunar cycles, eclipses, and planetary movements. The Mayan long count calendar, itself a triumph of temporal and numerical precision, emerges naturally from these geometrically encoded observations. In China, imperial cities from the Han to the Ming dynasty demonstrate a consistent orientation along a north-south axis, reflecting the cosmological principle of harmony between heaven, earth, and emperor. Palaces, gates, and ceremonial halls are carefully laid out to mirror celestial poles and cardinal directions. This alignment is not merely symbolic. Recent statistical studies, such as those by Shingley and colleagues, show that deviations from true north are minimal, often less than a degree, far beyond what could be achieved without careful geometric planning. Roads, walls, and waterways extend along these axes, turning entire urban landscapes into reflections of celestial order. Even in early Islamic civilization, geometry guided orientation toward the heavens. The Qibla, the direction of prayer toward Mecca, required precise astronomical calculation. Early mosques often employed observational instruments and spherical trigonometry to determine correct orientation. Scholars such as Emily Savage Smith have documented instruments like the astrolabe and sundial, used to align minarets and mihrabs with remarkable accuracy. The circle and its subdivisions, central to Islamic geometric decoration, thus also served a practical cosmic function, linking the earthly domain of worshippers to the broader cosmos. Across these cultures, geometry was never arbitrary. Recent studies have employed statistical analysis to measure orientation accuracy across hundreds of monuments. For example, a 2019 survey of Egyptian temples found that the alignment of over 50 major structures deviated from celestial targets by less than half a degree. Maya pyramid alignments, analyzed via LiDAR and photogrammetric data, show precision within a degree for solar zenith and equinox orientations. In China, measurements of Han Dynasty palace complexes reveal deviations as small as 0.5 to 0.7 degrees from the meridian. Even early Islamic mosques, spread across the Middle East and North Africa, exhibit Qibla orientations consistent with astronomical calculations far ahead of the available technology. These results underscore that geometric planning was a deliberate scientific process, not mere ritualistic imitation. Geometry encoded the rhythms of the universe, Stone circles, pyramids, observatories, and mosques were instruments for tracking seasons, lunar cycles, and eclipses. They allowed societies to predict agricultural cycles, schedule religious festivals, and understand celestial mechanics long before telescopes. Every axis, angle, and alignment reflects a dual purpose: practical observation and spiritual symbolism. Builders were translating the invisible choreography of stars and planets into stone, timber, and urban grids. The recurrence of celestial alignment across continents and cultures raises a profound question. Why was geometry always pointed at the sky? Was it a universal human impulse to connect with the cosmos? Or was it an empirical understanding, a rigorous observation that required precise measurement and calculation? Perhaps it was both, a fusion of science and philosophy, of mathematics and myth. In observing these monuments, we are reminded that geometry is more than a tool for construction. It is a bridge between human perception and the cosmic order, a language capable of encoding time, space, and meaning. From Stonehenge's solstitial stones to the Great Pyramid's stellar shafts, from Maya zenith passages to the north-south axes of imperial China, and the precisely oriented qiblas of early Islamic mosques, the lesson is clear. The sky was the ultimate template, and geometry was the means to translate it into enduring form. And as we trace these lines and angles, one question hovers in the mind of the observer. If geometry was so intimately tied to the heavens, what other cosmic knowledge might have been encoded in forms that we have yet to uncover? Across centuries and continents, a subtle thread weaves through human architecture and design, a thread that modern mathematics would only formalize millennia later. This is the language of fractals, recursion, and quasi-crystalline order, principles that describe how patterns repeat across scales, echoing the complexity of nature itself. Ancient builders, often dismissed as artisans or laborers, appear to have intuitively grasped these concepts, embedding recursive ratios and self-similar forms into temples, cities, and sacred spaces. In West Africa, Ron Eglash's pioneering research on African villages reveals that fractal principles guided urban layouts long before the formal development of chaos theory. From the recursive arrangement of courtyards and huts in Mali to the patterned streets of Benin, settlements exhibit a striking hierarchy of scale. Small clusters mirror the form of larger ones, and communal spaces echo proportions found at the village scale. Eglash demonstrates mathematically that these designs are not merely aesthetic. They optimize social cohesion, circulation, and resource distribution, showing that fractal logic was embedded in practical human life. In Southeast Asia, the lessons of recursion are just as vivid. At Angkor, LiDAR and photogrammetry reveal that satellite temples and gallery complexes echo the layout of central monuments. Distances, angles, and ratios recur, creating a fractal-like hierarchy that binds urban planning to spiritual cosmology. At Borobudur, the terraces of the Buddhist stupa replicate triangular and circular proportions across multiple layers. Each nested platform mirrors the higher level, and the alignment of stupas, balustrades, and relief panels obeys proportional relationships that resonate with both celestial observation and human perception of symmetry. The result is a recursive order in which the microcosm reflects the macrocosm, an architectural fractal that binds the monument, its surroundings, and the sky itself. This principle extends into the intricate world of Islamic architecture. Muqarnas, the stalactite-like decorations in domes, niches, and iwans, represent one of the earliest known three-dimensional fractal structures. Scholars such as Keith Critchlow and Salim al-Hassani note that muqarnas employ recursive layering, subdividing each surface into smaller units that repeat the geometry of the larger form. These structures are not only visually stunning, they manifest a deep understanding of repetition, proportion, and modularity, encoding complex mathematics into space and light. The aesthetic effect is amplified by shadows and reflections, creating a dynamic geometry that changes with the sun's movement, a living, breathing fractal. The recurrence of fractal-like design across civilizations finds a modern echo in the mathematical study of quasi-crystals and non-periodic tilings. Peter Liu, in his research on Penrose tilings, has demonstrated that many medieval Islamic patterns, giri tiles with 5- and 10-fold symmetries, are quasi-crystalline in nature. These designs, long admired for their beauty, adhere to mathematical rules that produce non-repeating patterns with local symmetries. When compared to Penrose tilings developed in the 1970s, the resemblance is striking. Ancient artisans achieved forms that mathematicians would only define centuries later. It suggests that pattern recognition, proportion, and recursion are intuitive aspects of human cognition, discovered independently in multiple cultural contexts.
Nature, too, provides a mirror for these designs. Benoit Mandelbrot, the father of fractal geometry, demonstrated that coastlines, clouds, tree branches, and river networks all obey recursive patterns. Human-built fractals, from African villages to Angkor Wat, echo these forms, suggesting that ancient architects observed nature closely and translated its principles into stone, wood, and brick. Galaxies, hurricanes, leaf veins, and neural networks all show repeated ratios and self-similarity across scales, implying that fractal logic is a universal principle accessible to human intuition without formal mathematics.
Fractal patterns also appear in religious and cosmological symbolism. In Hindu and Buddhist mandalas, the central motif radiates outward, each concentric circle and geometric division reflecting and amplifying the previous one. Sacred diagrams such as the Sri Yantra employ nested triangles and intersecting circles, producing visual recursion that aligns with both meditative practice and cosmic symbolism. The repetition of form, echoing through layers of geometry, creates a bridge between human perception and the structure of the cosmos, a physical manifestation of fractal logic. In architecture, this recurrence is not merely symbolic. Recursive proportions guide construction, circulation, and perception. In Borobudur, the repetition of triangular terraces and stupas produces sightlines that guide the viewer's gaze upward and outward, creating a layered narrative of enlightenment. At Angkor, satellite temples echo the dimensions of central monuments, reinforcing spiritual hierarchy and cosmic order through proportion alone. Early Abbasid mosques, too, use nested courtyards and minarets in recursive relationships, encoding a fractal-like understanding of space that unites the finite with the infinite. The convergence of these examples across continents and epochs raises a profound question. Were ancient builders intuitively mapping the mathematics of complexity? The evidence is compelling. Recursive ratios, fractal scaling, and quasi-crystalline tilings appear independently in Africa, Asia, the Middle East, and Europe. They manifest in domestic layouts, religious monuments, urban grids, and decorative motifs. The repetition is neither coincidental nor purely aesthetic. It reflects an understanding of how proportion, scale, and recursion can shape perception, social interaction, and spiritual experience. Modern science allows us to quantify and analyze these patterns. LiDAR, photogrammetry, and AI-driven pattern recognition uncover the repetition of angles, ratios, and layouts, revealing fractal structures invisible to the naked eye. Statistical analyses confirm that the recurrence of these patterns is far beyond chance. When combined with historical documentation, ethnographic observation, and mathematical modeling, the picture emerges of a global intuition toward recursive order, a shared human insight into the structures of nature and consciousness. Even in the realm of tilings and mosaics, this logic persists. Roman and Greek mosaics, Japanese asanoha, and Islamic giri tiles all exploit self-similarity and modular repetition. By interlocking shapes that echo across scales, these patterns create a sense of infinite continuation, hinting at principles now formalized in fractal geometry and complexity science. They demonstrate that human creativity, long before the advent of formal mathematics, could encode recursive order into tangible, enduring forms. The implications are profound. Across civilizations, fractal principles appear not as anomalies, but as a pervasive thread linking human cognition, perception, and creation. From the villages of Mali to the pyramids of Giza, from Angkor Wat to Borobudur, the evidence suggests that recursion, self-similarity, and quasi-crystalline order are universal aspects of the human geometric imagination. Builders were translating natural patterns into architecture, aligning human experience with cosmic and environmental rhythms, and encoding complexity in a way that resonates across millennia. And as we stand before these monuments today, one question lingers in the mind of the observer. Were these fractal forms consciously calculated, or were they the intuitive expression of a human mind attuned to the principles of complexity and the rhythms of nature? Whatever the answer, the recurrence of fractals, quasi-crystals, and infinite recursion offers a window into the extraordinary capacity of humans to perceive, understand, and manifest the mathematics underlying reality itself. In this convergence of intuition and modern science, the hero of our journey begins to glimpse a startling truth: that the ancient builders, separated by oceans and millennia, were not merely creating structures. They were mapping the hidden geometry of the cosmos, using proportion, recursion, and symmetry as their universal language. And in that recognition lies a revelation that challenges our understanding of history, mathematics, and the boundless potential of human insight. Across time and space, across deserts, oceans, and mountains, humanity has repeatedly returned to the same geometric forms. Circles, triangles, spirals, hexagons, they recur in Egyptian temples, Hindu mandalas, Greek spheres, Chinese cosmograms, and Islamic mosques. Civilization after civilization, separated by millennia and cultural chasms, arrived independently at the same language of proportion. It is as though geometry itself whispers across history, a universal code waiting to be read, a bridge between human perception and the cosmic order. The myths of ancient peoples speak in parallel motifs. The Egyptian creation egg, cradling the birth of the cosmos, mirrors the Hindu lotus unfolding its petals to reveal the universe within. Greek philosophers envisioned the perfection of the cosmos as spherical, a unity of heaven and earth. Chinese cosmograms depict the heavens as a circle, the earth as a square. The same interplay of symmetry echoed in Islamic architecture, where unity is expressed as a balance of proportion and repetition. Across these worlds, geometry becomes more than measurement. It becomes metaphor, theology, and philosophy. The shapes themselves are statements, a bridge between what is seen and what is eternal. In this way, humanity, through its architects, artists, and surveyors, has learned to navigate both worlds, the tangible earthly realm and the celestial universal realm. Each monument, each sacred layout, each tessellated tile represents a step along the hero's journey, a crossing from simple survival into mastery of abstraction, observation, and cosmic understanding. We are the inheritors of a vast geometric consciousness, transmitted not through language but through proportion, angle, and pattern. And yet the question remains, if this language is universal, where did it originate? Did human minds invent these forms independently, guided by perception and necessity, or did they tap into principles already written into the fabric of the universe? The consistency of ratios, the recurrence of the golden spiral, the precise alignment with solstices, the fractal repetitions across continents suggest a deeper order, a template embedded in reality itself. Geometry may not merely be a human creation, it may be the universe expressing itself through the medium of human hands and minds. If every empire built the same shapes, if spirals, triangles, circles, and hexagons recur across continents and centuries, the final question remains: were we building monuments to ourselves, asserting our place in the cosmos, Or were we, in some profound sense, building monuments to the hidden architecture of reality itself? And perhaps in that act, humanity glimpsed for the first time the sublime truth, that the universe in its infinite complexity had been whispering its patterns all along, and we, through stone and proportion, finally learned to listen. Thank you for joining us on this extraordinary journey through the universe on frontiers of infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us, where we unravel the darkest mysteries of space.